Hey, welcome back, everyone. So far, we've talked about special case of stochastic process, mainly focusing on the Bernoulli process and Poisson process, right? So again, today, as I mentioned earlier, I brought up a couple more exercise problems. So within the class hour, we're going to solve all together, okay? So this is the in-class exercise number 2. So we are going to answer these 15 different questions. And then right after that, I'm going to give you another problem set, okay? Okay, so let me see. Okay, so for the first 8 questions, I want you to identify and write down the probability distribution. So let's read the problem first. So vehicles arrive at a toll booth on a freeway. So at the average rate of 5 per minute in a completely random fashion. And the vehicles are counted and arrival times are recorded beginning at 12 noon. And then the 80% of the vehicles are cars, while the remainders are trucks, buses, etc. Okay? So we collect probability of being a car is 80%, right? So here we know that probability is 0.8, right? Okay, so what is the first question? Okay. Number of vehicles until the second vehicle, which is not a car. So we want to know the number of vehicles until the second non-car, right? So which probability distribution we have to use?
So this geometric, the first success until it failed. That's how I was looking at it.
Mm-hmm. So what about if I give you a hint like this? Let's say TK is the number of trials until the kth success. So in our case, the K is 2, right? So in our case, I would define T sub 2 as the number of vehicles until the second non-car. Then T sub 2 follows which distribution? Pascal distribution. Is that right? You remember Pascal distribution or negative binomial random variable is a generalization of the geometric, right? If k value is equal to 1, then that is the geometric. But in this case, k value is 2. So it's got to be Pascal or negative binomial. Does that make sense? Okay, then let's move on to the second question. An indicator x of n which is equal to 1 if the nth vehicle is a car, 0 otherwise. So what is this in this case? That is the indicator variable. If the nth vehicle is a car or non-car. It's like a single trial whose outcome is always classified as either a success or failure. It's not the binomial. If you have the single trial independently n times, then binomial random variable counts random number of successes within those n trials, right? So I'm talking about single trial, right? Whose outcome is either success or failure. So this is a Bernoulli, not the binomial, right? Does that make sense? So this is Bernoulli. You remember, when you consider the Bernoulli process, each random variable has to be independent each other, and each random variable in the Bernoulli process also follows Bernoulli distribution with the parameter p, right? And as I mentioned earlier, if you have this Bernoulli trial, single trial, n times independently, then binomial random variable counts random number of successes within those n trials. If you have this Bernoulli trial, Bernoulli experiment, over and over independently, then geometric random variable counts the total number of trials required for you to get the first success, right? You remember, right? And Pascal, or negative binomial random variable, counts total number of trials required to get the kth success. Okay? So number 2 is the Bernoulli, because we are talking about the single trial whose outcome is classified as either a car or non-car, success or failure, right? So this has to be Bernoulli. How about number 3 then? Number of vehicles until the first vehicle, which is not a car. So this is very similar to number 1, right? So it's talking about number of vehicles until the first non-car. So what is this? Geometric, right? So this time is geometric. So this time we are talking about t sub 1, right? Previously in number 1 is t sub 2. Right now we are talking about t sub 1. That is the number of vehicles until the first non-car, right? So this is got to be geometric distribution.
Okay, so I was going to say, can you, how, because to be there the same, except that, so you say t sub 2.
Right, because, yeah, first one, we are talking about the second vehicle, right? Yeah. Right now, we are talking about the first vehicle. So first success, and the number 1 is second success, maybe, okay?
Yeah.
It's not true. You gotta think just carefully, okay?
Now,
yeah.
I wasn't looking at the
Okay. What about number 4? Can you move on to number 4? Time of arrival. First vehicle. This time we don't need to distinguish if the arrived vehicle is car or non-car, right? We just want to know time of the arrival for the first vehicle. So what is this? Exponential. Excellent. So this is the exponential. You remember exponential distribution measures the time needed for the first occurrence, first arrival or whatever, right? How about number 5 then? Time of arrival of vehicle number 2. Along, right? Very similar to number 4. So this is 2 along. Remember, K along distribution measures the time needed for the kth occurrence. Okay. How about number 6? Time between arrivals of vehicle number 1 and number 2. You remember last time I mentioned if the arrival process follows Poisson, then the time between arrivals always follows exponential. Okay, so this is got to be exponential distribution. Okay. How about number 8 then? Number 7, I'm sorry. Number of vehicles arriving during the first 5 minutes. What is that? Poisson, right. This is Poisson distribution. So Poisson random variable is a count of the number of events that occur, right, during a given time period. So this is Poisson, right? How about number 8? The number of cars among the first 10 vehicles to arrive. Binomial? Is that right? Yeah, this is binomial. So binomial random variable counts total number of successes, random number of successes in a fixed number of trials. So this is got to be binomial. Okay? Does that all make sense to you? Okay? Okay, now let me give you a couple of minutes. Why don't you think about how to answer for questions 9, 10, 11, 12. Okay? This time, I want you to get the probability value, okay? Using certain formulation. Okay, let me change this a little bit. Okay. So then we're going to have some space to write up. Okay, so for number 9, how did you define the random variable to get the desired probability value? We want to know the probability that exactly 5 vehicles arrive during the first minute. So how did you define the random variable in this case? Anybody? How about n sub 1? What is that? Number of vehicles arrived during the next 1 minute. Okay? So, number of vehicles. Alright. During the next 1 minute. Okay? Then, this n sub 1 follows which distribution? Poisson distribution, right? And what is the parameter, lambda, in this case? here, up here, vehicles arrive at the average rate of 5 per minute. Is that right? So lambda's going to be 5 per minute. Okay? So this is going to be 5 per minute. Okay? So the desired probability is equal to, using the random variable that we just defined, n sub 1 as what? Is equal to 5. Is that right? Then how'd you get this? That's going to be E2 minus lambda t. T is equal to 1, right? And then lambda t, so lambda times 1 to the power 5, right? And then 5 factorial. So we're going to get a certain value. Of course, lambda here is 5, right? Anybody got an answer? I'm sorry? What?
0.1755.
0.1755. Okay. Mahmoud, you also got this number? Same number?
No, not yet.
No, not yet? Okay. Okay. So now let's move on to number 10 then. We want to know the probability that the first non-car is vehicle number 5. So we know that 80% of vehicles are cars, right? So 80% of vehicles are cars, right? We know this. And then how do you define the random variable in this case? You want to know how many vehicles arrived until the first non-car, right? So I define T sub 1 as equal to number of vehicles until you have first non-car. Is that right? Then T sub 1 follows which distribution? Number of trials until you got first success. What is that?
Exponential.
Why is exponential?
T sub 1.
But you still need to know whether that right vehicle is car or non-car, right? So the probability is involved, right? So which distribution you have to use? You remember last time? This part, Bernoulli process, always you're going to use what? P, probability. Poisson process, you always use lambda, right? So in our case, it's number 10, right? we want to know the probability that the first non-car is vehicle number 5. And we just defined T sub 1 is number of vehicles until you have the first non-car. So this gotta be geometric, right? And then in that case, probability of being non-car is, let's use 0.2.
Same as number 3. If you go up, number 3 is it?
Number 3? Yeah, sure. But in number 3, you just need to identify which distribution you're going to use. But at the moment, number 10, I want you to get the real value for the certain desired probabilities. Okay? So in that case, the desired probability is 1. Okay, what is that? Okay, so number 10, right, it's going to be probability, probability T sub 1 equal to 5, right? So 1 minus 0.2 for the first 4 vehicles, they are cars, right? But the 5th vehicle is non-car. So this is going to be the right formula, right? So what is this? So 0.8 to the 4th power times 0.2. What is the value for that? Point 08 19. Okay, thank you. Does that all make sense? Okay. Okay. Now let's talk about number 11. Probability that the second non-car is vehicle number 8. So this is very similar to the previous one, right, number 10. So in that case, intuitively, you're going to define T sub 2. What is that? Number of vehicles until you have second non-car, right? Of course, T sub 2 follows Pascal, right? Distribution. Again, probability is 0.2. Right? Then the desired probability should be T sub 2 equals 8. Is that right? Then I believe this is going to be 8 minus 1, 2 minus 1, 1 minus 0.2 to 8 minus 2, 0.2 to 2. Okay? How about number 12 then? We want to know the probability that 2 of the first 10 vehicles are cars. Of course, here is car or non-car. So you need to deal with probability, right? So we have to stick to the Bernoulli process. In that case, we're going to define n sub 10, number of cars within the 10 vehicle, right? Then n sub 10 follows which distribution? Binomial, right? With parameter n equals total number of trial 10, p equals 0.8. Probability of being a car is 80%, right? So the desired probability should be p n sub 10 equals 2, right? That's going to be 10 combination 2, 0.8 to square, 1 minus 0.8 to 10 minus 2. Okay? So we're going to get certain value for that. Does it make sense? Right? It's not difficult at all, right? Okay. Let me give you. How about number 13 then? We want to know the probability that the first vehicle arrives during the first 1/5 minute. So we want to know the time of the first vehicle arrived, right? So I would define T sub 1 as the time of the first vehicle arrived. Then, of course, T sub 1 follows exponential, right? Lambda is given as 5 per minute, right? Then the desired probability should be T sub 1 is what? First vehicle arrives during the first 1/5 minute. So T sub 1 has to be less than equal to 1/5. Does it make sense? Great. So it's going to be 1 minus E2 minus lambda, which is 5, and then T is 1/5. Okay? Oh, sorry, what is that? So does anybody got the answer for this?
0.6321.
Point, oh, sorry. 0.6321. Okay. Is there any other way to solve this to get this same probability value? How about if you use Poisson? How do you do that? If I define random variable n sub 1/5, which is n sub 0.2, what is this? Number of vehicles arrived during 1/5 minute. Then, of course, n sub 1/5 follows Poisson distribution. Is that right? In that case, mean rate would be what? Lambda t. What is lambda? Still 5 per minute, right? What is t? T is 1/5 minute, right? So 5 per minute times 1/5 minute, okay? Which is equal to 1. Is that right? So in that case, desired probability should be probability n sub 0.2 is greater than equal to 1, which is the same as 1 minus probability n sub 0.2 is equal to 0. Is that right? So, in that case, this is going to be, what did I do? Okay. This is going to be equal to 1 minus E2 minus lambda t. So, is it 5 times 0.2? 5 times 0.2 to power 0, and then 0 factorial. So this is going to be 1 minus E2 negative 1, right? Because this part is 1, right? And then this is also 1. So this is 1 to power 0 and 0 factorial. What is this value? This value should be same as this, okay? Any questions? So this problem can be attacked in two different views, right? Using the exponential distribution with lambda 5 per minute, and then Poisson distribution using the same lambda, which is 5 per minute. Okay. Okay. Of course, the parameter is lambda here, right? Okay. Okay. Now let's move on to number 14. So we want to know the probability that the fifth vehicle arrives during the first minute. So how do you define the random variable in that case? You want to know the time of the fifth vehicle. All right, right? So I would define t sub 5 is the time of fifth vehicle. Right. Okay. Then t sub 5 follows which distribution? The long distribution, right? Lambda is again same, 5 per minute. Then this desired probability should be equal to probability t sub 5 is less than equal to 1, right? Because we want to know the probability that the fifth vehicle arrived during the first minute. So it's got to be less than equal to 1 minute, right? And in that case, you remember the same, exactly same probability value can be obtained by using the Poisson random variable, right? So how do you do that? It's got to be n sub 1 is greater than equal to 5, right? Here, n sub 1 follows Poisson distribution. So, what is this probability means? Probability that the number of vehicles arrived within 1 minute, right, is at least 5. Okay? So, this is identical to this probability. Okay? But the nice thing, if you use the Poisson, then you should be able to compute it. Okay? Using any calculator. But in that case, for the L long, you do need a gamma table. Okay? That's why most of the time, if there is, whenever there is a L long distribution related probabilities, then usually we go by Poisson. Okay? So what is this? 1 minus probability n sub 1 is less than equal to 4, right? So what is this? 1 minus summation over E2 minus 5, 1, right? And then 5 times 1 to the power x, and then x factorial. Okay? Of course, x is equal to 0 to 4, right? Then you should be able to get certain value. Is that right?
So, isn't that 4 minus, 4 minus 1? I mean, 5 minus, okay. You have x equals 0, and then the top is what? 5?
0 to 4. This is 0 to 4. Because it is less than equal to 4. Sum over x equal to 0 to 4. Okay? Okay. How about number 15? So this is the last question for the in-class exercise number 2. We want to know the probability that the vehicle number 5 is not a car. So which random variable, which distribution we're going to use? So let's say X is the vehicle number 5. Then X follows which distribution? You just check whether the vehicle number 5 is car or non-car, right? So X follows Bernoulli, right? Bernoulli distribution with parameter P can be either 0.2 or 0.8 depending upon your interest, right? So it's got to be, the desired probability should be X equals 1, which is, let's say, 0.2, if this is 0.2. Okay? Of course, if you said probability is 0.8, then the desired probability should be X equals 0, right? Which is also 0.2. So either way, right? Either way does work, depending upon how you define the probability. Okay? Make sense? Okay, now I want to give you another problem set. Okay. I'm going to post this problem set later to our class Canvas homepage, so you should be able to access it. And probably, I'm not sure whether we have enough time to go over all of this problem. Just in case, I'm going to post the solution on our class homepage as well. Okay. So first of all, let me give you like a couple of minutes. Why don't you read through the problem description first? Okay. So let me load the problem. Okay. This is the first problem set, which is about the game of craps. So if you are not very familiar with this game, then here's the basic rule. On the second half of the problem description, okay, how to win this game, how to lose this game, maybe, okay? And then here's the basic rule. So why don't you take some time to read through all of this first. And then after that, we will try to answer this series of questions, okay? So let me give you, let's say, about 3 minutes. Okay? Does anybody play this game? The casino? I never played this game, but this is interesting, looks like. I believe first 3 questions are simple probability questions, right? If you read the rule of this game carefully, then it should be very easy to answer for the first 3 questions, I believe. Okay, so now let's work on that. Okay, so in preparation for a game of craps, you were asked the following questions. The first question A, what is the probability of winning at the first toss of the dice? So how do you win this game? If you go down here, here's how you win this game. If you roll a 7 or 11 on the first roll, or if you roll all of these numbers and roll the original number again before the 7 comes up. Because the first question asks you the probability of winning at the first toss of the dice. We need to know the probability that you're throwing a 7 or 11, right? On the first roll. So how many different ways you're going to throw 7 or 11? For 7, what is that? Sorry. So for 7, you draw 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1, right? So there are 6 different ways. And how'd you get? Is that 11, right? How'd you get 11? You can get 5 and 6, 6 and 5, right? That's the only way. So you have 2 different ways. So in total, there are 8 different ways that you can throw a 7 or 11 out of 36, right? If you throw a standard pair of dice, then there are 36 different ways. Different outcomes, sorry. So what is this? 2 over 9. So that is the, that is the winning probability, right? Probability of winning at the first toss of the dice. That is 2/9. What about question B? What is the probability of losing at the first toss? So go down to double check. So here's how you lose the game during the first toss. If you roll 2, 3, or 12 on the first roll, then you're going to lose the game. So 2, 3, 12. How'd you get 2? Just 1, 1, right? How about 3? 1, 2, or 2, 1? right? And then how about 12? 6, 6, right? So there are 4 different ways that you can lose at the first toss. So 4 out of 36, which is same as 1/9. Okay? So that is the losing probability at the first toss. Is that right? Okay. How about question C? If the first toss is 4, what is the probability of winning on the next toss? So again, go back to the winning rule. Here, if you roll a 4 during the first toss, and if you roll the original number, which is same number, a 4, again, before a 7 comes out, then you will win this game, right? So in that case, how would you get 4? 1, 3, 2, 2, 3, 1. So there are 3 different ways, right? So 3 out of 36, which is 1/12. That's the probability of winning on the next toss. Is that right? Those are simple probability questions. Okay, so can you move on to question D then? What is the probability of throwing a 7 or 11 at least twice in 6 throws of a standard pair of dice? So intuitively, which distribution do you have to use? Binomial, right? Because you remember binomial when the variable counts random number of successes within a certain number of trials, right? So if we define, let's say, n sub 6, that is the number of throwing a 7 or 11 in 6 throws of a standard pair of dice. Then this n sub 6 follows binomial distribution, right? With parameter n is equal to 1. Total number of trial, which is 6. What about p then? What is p? Huh? 2 nines, right? Where did you get it? Up here, right? The first one. You got this, right? So 2 nines is the probability here, which is from part A earlier. Is that right? And then the desired probability should be n sub 6 equal to, no, it's at least twice. So it's got to be greater than equal to 2, right? At least twice. So this is same as, let's say, 1 minus probability n sub 6 is less than 2. Then, you know, this is going to be 6 combination 0, 2 nines, 0. This is 1 minus 2 nines, 6 minus 0. And minus 6 combination 1, 2 nines, 1. This is 7 nines. And then 6 minus 1 becomes 5, right? So you should be able to get certain value, probability value. Any questions so far? Is it okay? Okay. Now, how about question E? Right, mean value. Okay. Simply asking you expected value of the random variable that we defined, right, earlier. Because n sub 6 follows binomial distribution, so mean value should be n times p, right? So n is 6, p was 2/9, right? 2, 3, so 4 over 3. That's going to be 1.333, right? So it's going to be 1.3 and dot, like that, right? Okay, what about F? What is the expected number of throws of a pair of dice required in order to obtain a 7 or 11? I think we've done this very similar problems earlier, right? So to answer for this question, we need to define another random variable, right? What is that? You remember? We defined T sub 1. What is that? Number of throw of dice required to get the first success, right? So there's the number of trials required until you obtain the first 7 or 11, until the first success, right? And of course, T sub 1 follows geometric distribution. Is that right? With, again, parameter, P is same as 2/9, right? We got this earlier. And the question asks you expected value of this random variable. Is that right? And what is that?
1 over p.
1 over p. So that's going to be 9 over 2. That's 4.5. Is that right? So any questions? I believe the second problem set is also very similar to what you've done earlier. So why don't you guys do this at home? I'm going to post the solution on our class Canvas website. So please make sure that you're going to compare your own solution to mine, okay? And let me know if you have questions or if you find some error later, okay? So it's got to be okay. It's not going to be that hard at all. So you should be able to get all of these answers, okay? Okay, so this is all for today. Thank you very much.